Steel bikes are flexy, aren't they? Everyone thinks they are. Even us at Starling, we've not talked about flex, but we've talked about compliance, about how the steel gives a little bit. But we kind of thought we'd actually apply some science to this and do some testing. Test one of our frames, measure some stiffness values and compare it against, in this case, it's a Nukeproof reactor. So we've got a jig set up. I'll talk you through what we do, explain what we're doing, and then we'll get some results, comparing the stiffness of the two different frames, and we've got some interesting results to tell you. So what we're going to measure is the lateral stiffness of the frame, so equivalent to a frame going around a corner. What happens as a rider goes around a corner? So as the bike goes around the corner, the acceleration, the acceleration acting on the rider pushes his weight sideways, which is then reacted out through the bike frame into the ground via the tyres. We've set this jig up to kind of represent that behaviour. We've got the frame fixed at the head tube and then pivoting around the bottom bracket, and then we're applying weights at the wheel rim in a place which is equivalent to where it would hit the ground in a real case. In terms of a jig setup, every test engineer would probably be pretty jealous because we've got a surface table which is the biggest, stiffest lump out there. This surface table that we use for aligning our frames isn't going anywhere. So straight away we've got a really good baseline to do this test around. The same with the head tube fixture. So the head tube fixture is an old lathe tailstock that we use for aligning our frames. So the head tube is very fixed in this position and it's fixed parallel to the surface table. At this point here where the bottom bracket is, we've got a puck which essentially keeps the frame so that the frame is perfectly parallel to the surface table. And then at this point here, we will probably see from another angle, we've got a whole load of weights hanging off the wheel rim at an angle. We've measured, just so you can see there, we've measured so that this position is equivalent to 66 head angle on this bike. This represents 90 degrees, so it represents the angle down to the ground from the bottom bracket, from the dropout. So this represents where the wheel would hit the ground. So what we're going to do is apply weights at this position, like I said, which represents the tyre hitting the ground. We've got this little bit of metalwork here, so this is holding it in that correct position. We apply the weight. We're using this height gauge. We measure the height to there, and then we'll take the weights off. And then we can remeasure, and you can see in that case it's dropped by about 15 mil, 10, 15 mil, or it's come up by 10, 15 mil. So that's the deflection that this weight's giving. These weights, out of interest, they are just a set of barbells, like James in the Workshop's barbells, but they add up to 20 kilograms. 20 kilograms is a reasonable figure for the side load you see on the bike. And I've actually chatted to EFB in Germany who do lab testing. They do their fatigue tests based on 20 kilograms, or factored up, but using 20 kilograms as the load they use for their lateral fatigue test. So it's a reasonable figure to use for the loading you will see on a bike in a corner. So we're going to do a number of tests. We've got this Nukeproof reactor frame, which is a similar frame to our Starling Murmur. I think this is 130 travel, similar chainstay length, similar head angle, geometry is kind of the same. We're going to do the same test with a Starling Murmur frame. We're also going to do the test, something else is we're going to do both with and without a shock, because there's a lot of talk about how shocks get destroyed by lateral side forces, and it's interesting to learn that data as we go along. So we'll do the test with and without shock. Another test we will do is independently we will work out the stiffness of the wheel. So if it turns out that both the stiffnesses are the same for the frames, but all the deflection was coming out from the wheel, you wouldn't learn anything. So we will measure the stiffness of this wheel actually on our mill over there, because again, that's another big solid bit of structure to help measure it. And in fact, it shows wheel stiffness actually isn't that important. The factor we don't take into account on this is all the other components, bars and seat posts and cranks and things like that, but we're interested in the stiffness. We also don't consider the tyre deflection in this test, but again, what we're trying to find out is the relative stiffness of different frames. A steel frame, one of our Starling steel frames, and this is actually a carbon fibre Nukeproof reactor frame. So as we said, the wheel stiffness is a component. So if the wheel was very flexy, it would dominate the overall system, stiffness of the system we're measuring. So we need to measure the stiffness of the wheel first to understand that. So we've actually set this up in our trusty old mill here. Again, this is a big solid lump of metal. This is going nowhere. It's a perfectly good test rig. We've got a shaft running through the axle, bolted into the bed, fixed into the head here. So that's very, very stiff. And again, what we're going to do is we're going to measure without weight applied and then with weight applied. And from that, we can work out the stiffness of the wheel from the hub relative to the hub. And we can use that to compare to the stiffness of the system when we do and see how much of a component of the whole system stiffness is. So let's measure it without. We'll use this height gauge here to actually measure the height. So we've put this little, it's actually used for marking out centres on stuff, or it's for doing big circles in steelwork. But we've mounted that to the rim, so we've got a good, nice reference point at the top that we can measure from. So I use this height gauge, and we'll get that. So it's just touching like that, and then we can read off the dimension. So that is 15.1. It's actually 15.1 dead. So let's note that down. 10. Okay, so we'll now do the same. We'll put the weight on, we'll measure the deflection, and we can work out what the stiffness of this rim is. Okay. Stop it wobbling. You can see it's not a lot, it's like 2 or 3 mil, but we'll get the proper number. 14.7.
Say it again.
14.72, say it again. So 14.72, so we take one from the other, about 1.3 mil. I'll get the calculator out, 1.42. So that tells us 20 kilograms of weight at this rim deflects it 1.42 millimeters. When we do the deflections with the frames, anything, say we get 5 mil deflection with the frame, then it means 1.4 mil of it is from the wheel, the rest is from the frame, so we know which component to compare versus the frames. Okay, so now we're going to do some testing of the stiffness of this frame, put the weights on the back. A couple of notes. When I was doing the wheel measurements earlier on, what I've noticed going from here to there is that this height gauge is in centimetres. So the numbers I were given, 14.72, 15.1, were actually in centimetres. So what it means is the deflection was about 4 mil. It's 3.8 mil for that wheel, 0.38 centimetres. The other thing to note is this Nukeproof frame was kindly lent to us by Friction Cycles in Bristol to do this test. It was a customer bike. I think it's barely ridden. It was an ex-demo bike, so there is no bearing play in it, and that's quite important because on a linkage bike, as the bearings wear, you'll develop play, and that would be seen as much more deflection here. But the bearings are all really good condition, all super tight, so that's worth mentioning. So what we'll do is we will do the measurement without the weight, do the measurement with the weight, then we'll do the same and we'll put the shock in place, and then we'll do the same 2 tests with the Starling frames. Okay, so let's just get this right. Okay, so that's good. So that is 17.32. So Nukeproof without shock, 17. Oh no, that's unloaded, 17.32. It's also worth noting this one where we're doing no shock, we've got a dummy shock on, so it's held in the right position, so the swing arm can't move. So that's not adding any stiffness, but it's holding everything in the right place. So we'll do the same again. We'll put the weights on. Okay, that's pretty good. So that is 15.07. So let's get my calculator out. 17.32 minus 15.07 equals 2.25 mil. In fact, let's do it all in centimetres so I don't get 2.25. So that's interesting. So we're seeing I'll put it into millimetres because my head works better. So it's 22 mil deflection, and what we were seeing before that, 3.8 mil, roughly 4 mil deflection comes from the wheel. So the frame is actually adding a lot of the compliance. So the wheel is 4 mil, the overall system is 22, so that means the frame is about 18 mil of the overall deflection, which is interesting. So the wheel doesn't dominate, the frame dominates to the flexibility of the frame. So we'll now do the same frame but with a shock in and see if that affects the stiffness of the system. But not too tight. So we'll do deflection at the rear wheel unloaded first. So let's get and that is 17.3.30. So Nukeproof with shock unloaded, 17.30. So let's do it loaded. Don't drop any weights on my toes. That is 15.80. Yeah, 15.80. So there you go. So with the shock, it's 15.80. The shock has reduced the deflection by 0.8 of a mil, 0.7 of a mil. That means the shock has increased the stiffness of the deflection at this point. Overall, that has contributed to the stiffness of the frame as a whole. Right, so we will swap this frame out for the Starling, do the same 2 tests with and without shocks, and then we've got a set of numbers and we can look at the numbers and talk about those. Right, this is the Starling frame we're going to use. It's a Murmur frame. This is actually a test frame that went to EFBE in Germany. This frame has been through a full, I think, Category 4, Category 5 test at EFBE, but that shouldn't affect our stiffness test here. Nothing, there's nothing that will make it more flexible. So, right, we'll swap these 2 frames out and then do some measurements. Put the Starling frame into the jig, unloaded, without a shock, we can take a measurement. Okay, 17.34. Without shock, 17.34. Again, that's really good. The unloaded is 17.30, 17.32, 17.34. Tiny variation between the frames unloaded. So that's good sanity check that the unloaded is a sensible number. Okay. Let's see. 15.72. 15.72. So 17.34 minus 15.72 equals 1.62 mil. 1.62 mil. That's centimetres. Fucking centimetres. There you go. So we get 1.62 mil centimetres deflection for the Starling without the shock. The Nukeproof without the shock was 2.25 centimetres. So in fact, this frame is stiffer than Nukeproof for this lateral load case. But let's do the with shock case, and then we'll talk about it. Nice and tight, but not too tight. Starling frame with shock, do unloaded value. That is 17.33. So again, that's really good. All the unloaded are within 0.05, well, within 0.02 of each other. Try not to drop it on my toes. Wobble in, and then okay, and that is 15.97. Get my calculator out. 17.33 minus 15.97 equals 1.36 mil. So again, interestingly, 1.36 mil for this configuration compared to 1.50 mil for the Nukeproof. So this is actually a little bit stiffer than the Nukeproof. So from the numbers, the carbon Nukeproof frame is actually a little bit less stiff than the steel Starling, which we didn't expect. We'll go through the numbers in a bit. So there's got to be some other behaviour. So we've kind of been bouncing the frame like this, or bouncing the rear wheel and seeing how the whole frame reacts. So maybe that is what people are feeling. It's really difficult to show on TV. You know, we're bouncing it up and down on TV, on video. Okay, I'm getting ahead of myself there. And it's so difficult to compare, not having them next to each other, but my general feeling is this bounces for a little bit less time than the steel frame. It's got a little bit more damping, you could say, in it, but it's very difficult to say. So perhaps that's a field for a bit more exploration, but we'll do this a few times because it's interesting. Should I draw a knob?
Yeah, go for it.
Did you see somebody did the world's biggest Strava knob? Bloke in Wales basically did like a 500k journey to generate a massive knob. Okay, so we've done all the testing. We'll write up the numbers on this board so we can talk them through as we go along on this lovely whiteboard. So the first test we used the wheel on the mill behind us. So the loaded value was 14. Well, all the measurements were in centimetres because we used the height gauge, but I'm going to convert them to millimetres because my head works better in millimetres. So 147.2, 147.2. The unloaded value was 151.0. So the deflection was 3.8 millimetres. 3.8 millimetres. The next one was the Nukeproof carbon frame. Nuke carbon. First of all, with shock, 158.0, and the unloaded was 173.0, 173.0. So the deflection was 15 millimetres, 15.0. So what we need to do though, because some of that deflection includes deflection due to the wheel, we need to take off that 3.8 from the 15.0, and then that gives us the frame component. So if we do 15.0 minus 3.8 equals 11.2. So the number here is 11.2 mil. So if we do the same here, but without shock, so Nukeproof carbon without shock, 50.7, 50.7, 173.2, 173.2. So again, these values here should all be consistent because it's unloaded, it's just the jig it's just the frame in the jig. So it's good, it's a fraction of a mil out. The delta was 2.25 centimetres, so 22.5 centimetres, so 22.5, 22.5 millimetres minus 3.8 equals 18.7. So the first thing we notice, the stiffness with the shock is almost double what it is without the shock. So putting the shock into the frame has reduced our deflection by 7 mil, which is massive. So the shock is effectively it's a load path for that lateral load, and it's acting as a stiffness component to the frame, which is really important. That's a really important thing to find out. This is why lots of shocks get damaged from side load acting on them, why shafts wear, various frames of braking shocks. So there's this belief that having a linkage removes that loading, but we'll see what we get with the Starling, but there we're getting like 30, 40% of the load being taken by the shock. So let's do the same for the Starling. We'll do it in a different colour. So Starling, let's do with shock first, which is that one, 159.7. That one is 173.3, 173.3. The delta is 1.36, 13.6 because we're doing millimetres. And if we do 13.6 minus 3.8 for the wheel, gives us 9.8. 9.8. So we're comparing this with this. So the Starling with the shock in is seeing almost 10 mil deflection, the Nukeproof 11.2. So that is showing that the Nukeproof is more deflection, it is less stiff, it is bending more under load than the Starling. But they're very similar, it's like 10% different. But, well, let's do a thing. Number 8 divided by 11.2, or minus 1. So it's 12%, that's 12% stiffer, plus 12 to the Nukeproof. We'll do the same without the shock, without. So 15.72, 157.2, 173.4. Again, all of these within 0.1 of a mil, well, 0.4 of a mil, plus or minus 0.2, which is good. Deflection 16.2. 16.2 minus 3.8 for the wheel deflection gives 12.4. 12.4. So again, if we compare it in this case, the Starling is massively stiffer than the Nukeproof. So if we do 12.4 divided by 18.7, 33%, plus 33%. But that's obviously not a real case because you don't ride a bike around with a shock. But what it shows... Yes, you do. Yes, yes, you do. That isn't a real case because it hasn't got a shock in. Yes, very good, Jamie. So what that's showing here, if we did the difference between that, so 12.4 divided by 9.8, so that's 26%. So 26% of the stiffness, we'll just write it here, is through the shock. Whereas we do this one, yeah, 59%. No, it's the other one minus that, one minus, 41%. So the shock on the Nukeproof, that's a really interesting finding. But anyway, so really the numbers are interesting is with the shock, the 9.8 versus 11.2 and this 12%. So the Starling is a tiny bit stiffer, 10% stiffer than the Nukeproof. I suppose we didn't expect that. As Starling, we've actually talked about the compliance of steel frames and how that contributes to the ride feel, but this testing is showing us that isn't necessarily the case. I'd kind of argue plus or minus 10% is probably within the sort of variables of the test and the variables of the differences between the frames. So essentially our bikes are similar stiffness to the Carbon Nukeproof, and the Carbon Nukeproof is a bike that has had fantastic reviews, and we've actually scoured through the reviews. Not a single review says this bike is Flexy. So whereas reviews of the Starlings have said, in some cases, the Starling has got a flexy back end. So there's something odd going on here. And I don't really know what the answer is. I think we touched on it briefly when we looked at how the swing arm behaved as we bounced it. But I think my opinion, this is an opinion really, is that there is a difference in feel between a steel frame and a carbon frame. And because general belief out there is that steel frames are more flexible, that difference in feeling, people have concluded, is a reduction in stiffness. But our numbers are showing otherwise. Obviously, this is just one set of numbers, but I'm pretty happy with the test we've been doing. There's nothing major. Let me know if you can pick a big hole in it, but personally, I can't see it. Yeah, it's interesting, isn't it, Doc? So, really, that's the conclusion. Our testing, which we think is reasonable, shows our bikes are equivalent stiffness, if not stiffer than an equivalent carbon frame. So there must be some other factor we're not aware of. We need to think about what it is. I think it's potentially feel. I think the other thing that's really interesting is that our frames don't take a lot of load via the shock, which is why we don't see wear of the shocks, whereas this Nukeproof takes a significant amount of the load via the shock, which is why linkage bikes tend to destroy bikes, even though intuitively people don't believe in that. So there you go. Can't think what else to say. Interesting. So I think that's really interesting. Obviously, let us know what you think. Let us know if you've got any ideas about what the difference, what caused these differences. Let us know your own personal experiences. If you've got any data you can help add to this argument, yeah, let us know. Put any comments you need to. I'm sure this will go up on both social media and YouTube. There'll be opportunities to comment there. Send me an email if you want. Also, if you've got any more ideas for videos that we can do, let us know. I'm not going to say like and subscribe, but I have just said it. So yeah.
Done.
Okay, that's really good. I'll tell you what, let's do this.